This is page 6 of the synchronization notes. Now we're going to talk about a general solution for barrier synchronization. And this solution that I'm going to cover comes from the little book of semaphores, and this is by Alan B. Downey, who's a computer science professor at Olin University in Massachusetts. And it may have been a little book of semaphores. It's grown quite a bit now. It's about 300 pages as a PDF. He publishes it free, so you can just search for it online and you'll find it from Green Tea Press. While I was looking that up, I realized that he's also done an a free operating systems textbook called ThinkOS, and it's aimed at programmers, so I'm going to be taking a look at that. So let's look at this solution. So we have parameters. So n is the number of tasks, and we're going to use a variable called count, and it's going to be the number of waiting tasks. So when a task arrives, if it's not the last one to arrive, it's going to wait. So we need a way to track that number. And because count is going to be modified by multiple tasks, it's shared data, and so we need to protect accesses with a mutex semaphore. So we're going to create a semaphore called mutex. So this is a semaphore to protect accesses to the count variable, and the tasks need a way to block until the last task has arrived at the barrier, and so we're going to use another semaphore for that, and we'll call it the turnstile semaphore. So used to block until the last task arrives at the barrier. And before I go any further, this is a more complicated use case than we've seen so far, and I would suggest that if you're still shaky on what semaphores are, that you review the videos for pages 1, 2, and 3 of the notes. It's important to get that concept that a semaphore is really just like a counter. It can go up or down, but you use these special functions to access it, wait and signal, and that if a task tries to decrement or wait a semaphore that's at a count of 0, that task is going to block until it gets signaled by another task. That's the key thing. So let's look at the steps that would be taken to do this, to implement this. So this is just very general terms. So we're going to have some initial values, and they are count is 0, so initially no tasks have synced on the barrier yet. Mutex, we need that's that lock semaphore, and it needs to be initialized to 1 so that the first task to access it can decrement it or wait it without blocking, and when it's done it will signal it to let another task through. And then the turnstile semaphore, we want the first n-1 task to block, so when they wait on it we want them to block, so its initial value should be 0. So that's step 1. Step 2 is every task that comes along should increment count. So increment count, and I'm going to add more to that line in a minute. Step 3, all the tasks will do as well, and this is the turnstile. So the first thing they will do is wait on the turnstile, then signal turnstile. And if we leave this description as I have it right here, all n tasks will increment count, and then they will all wait on the turnstile, and you'll have n block tasks. So they've at least synchronized at a point, but there's no way for them to proceed. So we need to do something to fix that. We need one of them to signal the turnstile to let the first one through. So I'm going to add to step 2 that the last task should signal the turnstile. So what that'll do is the last task will signal a turnstile. That's going to unblock one of the tasks that had been waiting on the turnstile. When they unblock, they will then signal the turnstile, which will unblock another waiting task. And so you'll have this kind of chain reaction of one task unblocking, signaling another task, and unblocking them, and so on. And that's where the turnstile name comes from. So let's outline the pseudocode here. So we are going to have our count variable. It's an integer, and it's going to be initialized to 0. And we're going to have two semaphore, they are variables, but two semaphores. So mutex is initialized to 1, turnstile is initialized to 0. And this is the first case in our pseudocode where we want to create a function. So I'm going to just show that by giving it a name. Let's call it barrier, and brackets there to indicate that it's a function that can be called. And so this is going to increment steps 2 and 3. So before we increment count, that's shared data. That's a critical section, so we need to acquire the mutex. So to do that, I'll just indent this to show it's part of the barrier. We will wait mutex. So this is the acquire step. And once the task has acquired the mutex, it knows that it is the only task that's modifying count. So it can go ahead and increment count. And then we need to add that test to see if it's the last task. So if count is equal to n, then we want to signal the turnstile. And that's all step 2. And now once we're done step 2, we're not modifying or reading count anymore, so we can release the mutex by signaling it. So signal mutex. So that is releasing the mutex. And you'll notice that I indented those 3 lines between wait mutex and signal mutex. In your code, you don't have to indent them, but it just helps to visually identify that you are holding a mutex while you're executing those 3 lines. So it's just really a hint to the programmer, so for readability's sake. Okay, so that's step 2. Step 3 is also part of the barrier code. So we need to wait the turnstile. So wait turnstile, and then signal turnstile. So all of our tasks are going to block here, but one of the tasks, the last task, is going to signal the turnstile, which will unblock one of the waiting tasks. And once they unblock, then the next thing that they do is signal the turnstile, which unblocks another task. So that's the barrier code right there. And so the code for this, hopefully you can fit this on one page, would look like this. So say we've got task 1 to task n. They're all going to look the same. They will loop forever, and inside there they'll do some work, and then they will invoke the barrier synchronization to wait for all the other tasks to reach the same point. I'll copy this over for task n. And then they can continue. Now I put this barrier in a loop, and we're going to see that there's actually a problem that this barrier is not actually reusable, but we'll address that.